Generative AI systems have made leaps and bounds in the past few years, but will they be able to replicate and eventually replace human beings? We can answer this question along three different axes: functionally, in terms of their capabilities; economically, in terms of replacing all human contribution to work in the economy; and spiritually, in terms of our inherent value as human beings. So what's the answer?
Written in historical records, documented in Tacitus and Josephus. For those who don't believe us, check the marks of architecture written on a fetus. Neural nets and error correcting codes complete us.
Chaos theory.
Reality.
So imagine we wanted to create a text prediction engine where we begin with a random word and then conditioning on that word, we produce the next word. So Claude Shannon, the father of information theory, did that exact experiment in 1948. And he came up with this text here: the head and in frontal attack on an English writer, that the character of this point is therefore another method for the letters that the time of whoever told the problem for an unexpected. Okay, so that's not really coherent. And it's using this bigram method, so the second order word approximation, where we begin with a word like frontal, and given the word frontal, there's only so many words that could follow it, right? So such as frontal assault or frontal attack. And so we predict the next word as attack. And so doing that, he produced this block where there's actually little local pockets of coherence within it. So for example, frontal attack on an English writer, if we were to read that, we might be concerned for a colleague in the English department. So that is just conditioning on the previous word. But what if we conditioned on the previous 3,000 or 30,000 or 300,000 words? Well, we would end up with something like chatgpt, which could produce poetry, even poetry about Dallas, Texas. In Dallas, where the skyline's grand, you'll find tall towers across the land. The traffic's fierce, the streets are wide. You'll need a map to get inside. Okay. Not the best poetry I've ever read, right? It's a little bit doggerel. However, it is recognizable as poetry. So generative AI systems can do a lot of things. They can produce poetry in prose. They could create lesson plans and generate recipes. They could summarize text. They can write functional computer code. And they didn't do this so well, a year ago, but now they've gotten pretty good, right? Vibe coding is a real thing. They could explain concepts and answer questions from documents. They could do what looks like logical reasoning and rational inference. I put an asterisk on that, and we'll see why in a minute. And unfortunately, they can generate mis and disinformation. So if you asked early GPT systems about the Russian space bear program, it would give you a whole list of space bears, the times they were in space, what their missions were like, and link to articles talking about them. The only problem is there was never a Russian space bear program, right? And then we can all remember the Biden robocall scam that happened during the election, where someone who sounded like Biden was telling voters not to actually vote. Okay, so these are problems with these systems. There's also another class of systems. These are called diffusion models, which allow you to turn text into images. And so you've all seen many examples of this. We can generate very realistic looking humans using these systems, or realistic landscapes, or even fantastical landscapes. In addition to this, we now have text-to-video models, such as OpenAI's Sora, which was released in 2024. And here's a still from it, right? It looks maybe like a Wes Anderson film. But we have even better text-to-video models now, such as Google VO3, that has been blowing up the internet. You can probably find examples of that if you search. So this raises the question, how can we turn text into video? And how can symbols encode knowledge about the real world? So there are two critically important ideas in the world of large language models. The first being attention, which we're not going to talk about, and the second being text embedding. And so what text embedding does is it uses relationships among words to encode certain aspects of semantic information. And so what do I mean by that? So imagine that you're reading a book that you don't know a word in, right? That word, the way that you would try to understand that other than looking it up, is you could look at the words nearby and try, based on the context, using context clues to try to understand what that word means. That works because words that are similar are often used in similar context. Text embedding does something similar. It looks at statistical correlations among words and then turns those relationships into vector spatial relationships. So for example, if I do a text embedding on a group of words that include fish, bear, and wolf, we'll see that spatially they will end up near each other and form a cluster. And also things like salad, stew, and fish would form a cluster. And it's interesting because fish is used in two different ways. It's used as a food and as an animal, and this shows up within the text embedding. So large language models and diffusion models are both types of deep neural networks. They encode relationships among symbols and pixels, turning words into vectors and text understanding into a problem of mathematical geometry. But they are fundamentally based on statistical correlation of symbols, among symbols. And so what that means is they know what is similar to what, but they don't know what anything actually is. So given their capabilities, let's look at some of their functional limitations. So it turns out, remember when I put that little asterisk next to LLMs could reason and do logical thinking? They actually cannot. So there was work that came out in 2022 from the STAR Lab at UCLA by Zhang et al. On the paradox of learning to reason from data. But what they found was that models with near perfect accuracy on reasoning tasks would plummet in performance when you changed the way that the problems were presented. But this doesn't make sense if the systems actually learned propositional logic, if they learned to reason, because it shouldn't matter how you present a problem. It shouldn't matter if you got that problem from a friend or if you got it from a textbook. But what they found was the system was actually doing statistical pattern matching. It was using statistical features to try to make predictions of what would be true or not. And so in that case, the training distribution becomes vitally important. Further work from 2024 confirmed this by Mirzadeh et al., which showed that adding irrelevant information to math problems would drop the performance of state-of-the-art reasoning models by up to 65%. And this is again because the systems were doing statistical pattern matching. They weren't actually doing mathematical reasoning. And so these are systems like GPT-4o, O1 Mini, Llama 3B. So here's an example of one of the problems. Oliver picks 44 kiwis on Friday, then he picks 58 kiwis on Saturday. On Sunday, he picks double the number of kiwis he did on Friday. But 5 of them were a bit smaller on average. So this is where the irrelevant information comes into play. How many kiwis did Oliver have? So both O1 Mini and Llama 3 8B gave the incorrect answer of 185 because the systems thought that you would have to deduct 5 of them because of the irrelevant information. However, the correct answer is 190. There's a further limitation of LLMs, which is that models trained on their own outputs can't actually improve. And so there was a team, Shumailov et al. In 2023, which found that if you take a system, train it, and then have it produce text, when you train a new system on that text that was produced, it's going to be a little bit worse than the previous system. And so if you keep chaining this forward, you train a system, have it produce text, train a new system on that text, that system produce other text, train yet another system. So by the time you get to the 8th or 9th generation, the systems become mumbling idiots, right? And there's a reason for this mathematically. It has to do with subsampling, because you're never going to get a full representative sample when you're doing finite sampling. The tails of the distribution are going to fall off. You're going to end up oversampling the mode of the distribution. So we can see an example of this in the paper, where in the first generation, we have a prompt about architecture, and it gives a coherent response in terms of architecture. So it talks about revival architecture, such as St. John's Cathedral in London. Okay, I'm not an architect, so I don't know if it's correct, but at least it sounds reasonable. But by the time you get down to the 9th generation, I'm just going to read this, it talks about perpendicular architecture in addition to being home of some of the world's largest populations of black-tailed jackrabbits, white-tailed jackrabbits, blue-tailed jackrabbits, red-tailed jackrabbits, yellow-tailed jackrabbits, right? So literally it goes down a rabbit hole because it's oversampling among the modes of the distribution. So this is important because as LLMs get more proficient, people are populating the World Wide Web with artificially generated content. And so future systems are going to have this exact problem, which is what prompted this research in the first place. Okay. So in addition to undersampling, there's also a fundamental information theoretic reason why model collapse happens, and that's because of the data processing inequality. So the data processing inequality, to give you a rough idea, states that clever processing cannot increase the information content of a signal beyond what's already contained in the signal. And so what that means is that if you start off with the English language and you take a finite sample of that and try to train based just on that sample, you're always going to end up with an imperfect copy of the English language. right? And so as you take this one step, you're losing something. And so if you keep doing this step repeatedly, each time you're losing a little bit more information about the English language. Okay. And this happens not just for language models trying to model English text. This happens if we're trying to replicate a human being, right? So every training data set is fundamentally a finite snapshot of what it means to be human. So you can imagine if we traveled back to 1725 and took all of the text that had been produced to that date, all of the cultural artifacts, all of the architecture, etc., we would get a snapshot of what it means to be a human being, but that finite snapshot would also leave a lot out. By analogy, if we did that same thing in 2025, we would also fundamentally have a finite, incomplete snapshot of what it means to be a human. But we just saw with the data processing inequality that your model of a human is only as good as what is already present in your training data, right? And so if you start off with a real human, you take a data sample which is incomplete, and then you try to replicate that human based on that training data, you're always going to fundamentally miss out on aspects of humanity. And so for this reason alone, we can confidently say that as long as our data snapshots miss out on fundamental aspects of what it means to be a human, then we're not going to be able to create and replicate a human based on this finite training data. So the things that we looked at so far are things that may or may not be able to be overcome with a little bit more training data, maybe different system architecture, but there are also some aspects which are perhaps a little bit more fundamental. And one of those is the divide between syntax and semantics, namely that syntax is independent of truth and meaning. For this next section, we're about to get a little bit more technical, and so I wanted to give you some vocabulary before we begin. So there are two words that I want you to know about. And the first one is syntax, the second one is semantics. So syntax deals with the surface level structure of words, their form and how we manipulate them. Semantics deals with the meaning and the truth value behind the words, what they refer to. And the point I'm going to make in this next section is that syntax does not equal to semantics. And just having access to the syntax side of things does not necessarily give you any insight into the meaning or the truth value of what those symbols represent, okay? This is not a brand new idea. It goes back to at least 1929, where René Magritte, with The Treachery of Images, the famous painting that is of a pipe, which says, translated from French, "This is not a pipe," right? And there's also the well-known saying, "The map is not the territory," which embeds the idea that the representation of a thing is not the same as the thing itself. So formal syntactic systems were developed to allow proof checking without thinking. So there's this comic called Logic Comics that has Bertrand Russell sitting with Alfred North Whitehead listening to David Hilbert. And Hilbert is talking about the mechanization of formal logic. Namely, he wants to make mathematics so precise that a machine could carry out the operations. And the point of this was to remove the subjective human element from rational thinking. So to try to build a deduction system that a machine could carry out. However, this turned proof systems into formal games, where the syntax, namely the symbols and the game rules, were separated from the semantics, the truth and meaning that underlied them. Kurt Gödel in the 30s showed the limitations of such formal systems. Namely, he showed that any formal system capable of representing arithmetic would always have true mathematical statements that could not be proven within the same system. And he did this in kind of a clever way. And so his way was to come up with a statement that was essentially something like, "The statement is unprovable." And then he encoded that statement as a mathematical numeric formula within his system. So then we have to ask, what if you could prove that statement within your system? Okay, so if you could prove that statement, then the statement becomes false because the statement says this statement is unprovable. So what you will have done is shown that your formal system can prove false statements. And you don't want that. Because if you could prove one false statement, you can prove all the false statements. You could prove all statements. Okay, so the other option is that we cannot prove this statement inside of our system, which makes the statement true. And so what it means is that you have a true mathematical statement that you cannot prove within your system, which was Kurt Gödel's conclusion. And so what that means is that syntax is independent of truth and meaning. Syntax is not the same as semantics. Formal logic systems are divorced from meaning, and they're that way by design, by construction. Syntactic proof systems can model rational processes, but they are not rational processes themselves. They are just formal symbol manipulation games. Kurt Gödel showed us that the proof process does not equal the truth process. And we have these notions in formal logic, such as soundness and completeness of systems. Those notions, which are highly important, are fundamentally rooted in this divide between syntax and semantics. They do not have any meaning unless you can separate syntax and semantics. So what does that mean for us in the AI world? Well, it turns out that AI systems are trapped on the syntax side. And so others like John Searle with his Chineseroom argument and emilybender, they've made this point forcefully, that just having access to symbol manipulation, just having access to syntax does not get you to semantics and meaning. So I can confidently say that there are fundamental limitations to generative AI systems now and in the future, and reasons why we shouldn't expect them to faithfully replicate human beings. And those diffusion models, which produce the really impressive images, turns out they don't actually have any understanding of biology. So the same systems that could produce the impressive looking images can also produce body horror by accident. So you have these images of kids doing jujitsu, but if my kids were ever at a gym where there was a kid twisted up like a pretzel like that, we would yank them from the gym so quick, right? Or you can have these images of men doing acrobatics where you have another man growing out of his legs, right? And so this shows that the system doesn't really understand how biology works. However, it knows about correlations among pixels. So if pixels are related to other pixels, that's what it's going to produce. So those are some fundamental limitations in terms of functional capabilities. But what about economic impacts?
Chaos theory.